Okay, so all semiconductors we can classify into two groups, mainly intrinsic semiconductors and extrinsic semiconductors. So intrinsic semiconductors are the one with pure substance. So an intrinsic semiconductor is pure semiconductor with no impurity or defect. Example, silicon or germanium. So in intrinsic semiconductor, we know in normal temperature, even in the room temperature, due to thermal energy, the bond will break and then electron holes pair will create. So this creation is pairwise creation. That means if one hole is created in free electron is created, means one hole is also created, right? Okay. And in intrinsic semiconductor, we know that hole concentration and electron concentration, free electron concentration, both are equal. Okay, right. And also in intrinsic semiconductors, for the electrical conductivity, both holes and electron will distribute. Okay, and here's the graph we discussed in the last class. And extrinsic semiconductors are modified by adding control amount of defect or impurities into intrinsic semiconductor. So this adding defects or impurity to an intrinsic semiconductor, this process is known as doping, right? So due to the doping mechanism, we can classify further in extrinsic semiconductor as N-type and P-type. Now, N-type semiconductors are made of doping with elements from group 5 in the periodic table. And since group 5 elements have 5 electrons in the outermost shell, so 4 of these electrons makes bond with the neighboring lattice atoms, and then there will be remaining electron that will be ionized and it will be free in the lattice. So the phosphorus, suppose we dope with phosphorus, then phosphorus become a positive charged ion, right? Because it's losing of electron, so the phosphorus become positively charged ion. So since this phosphorus atom gives an electron to the lattice, it donates an electron to the crystal. Therefore, we say that's a donor atom. Okay. So donor atoms become positively charged. Okay. So in P-type semiconductor, since this donor atoms gives one free electron to the crystal, so the free electron concentration is greater than the hole concentration. So in N-type, majority carriers are free electrons and minority carriers are holes, right? Because there are more electrons than holes, therefore majority carriers are electrons. So electrons are negatively charged. That's why this type of semiconductor is known as N-type. N refers for negative, right? And P-type semiconductors are made of doping elements from elements of group 3 periodic table, such as boron, aluminum. So this boron, aluminum, they are in group 3, so they have only 3 electrons in the outermost shell. So they can provide electrons to make bond with the only 3 neighboring atoms. Suppose now as in this one, we can see the borons can make bonds with 3 germanium atoms, and there is a deficiency to make a bond with this neighboring germanium atom. Right? So therefore, there is an incomplete bond. So this incomplete bond can accept an electron from the crystal, accept an free electron. Therefore, this boron atom is known as acceptors. And if they accept the electron, if it accepts the electron and then completes the bond, then if you consider the boron atom, it will gain a excess electron. So therefore, it becomes negatively charged. So remember, always these acceptors are negatively charged. Okay, donors are positively charged and acceptors are negatively charged. Okay, right. So in N-type semiconductor, electron concentration is less than the hole concentration, right? because we know in intrinsic semiconductor, if it's intrinsic semiconductor, there will be equal number of electrons as well as equal number of free electrons. The free term should be there, or conduction electrons. There in intrinsic semiconductor, equal number of free electrons and holes will be there due to thermal agitation. So the thermal agitation is pairwise production, because if one electron is created means one hole is also created, right? So now if we dope with boron, what happens? Boron will accept an electron from the crystal and fill the bond, and then it becomes a negatively charged ion. So then the crystal lose one free electron. Therefore, in p-type semiconductor, hole concentration is greater than the electron concentration. So therefore, this is known as p-type. So p refers for positive p-type, because holes are considered as positive charges, right? So here majority carriers are holes, therefore it is p-type semiconductor. Anyway, in an extrinsic semiconductor or intrinsic semiconductor, so the total charge will be always, net charge will be neutral. Now suppose if you consider the this crystal, right? So if this accepts the electron from the crystal, right? So this boron atom becomes minus charge, but there will be somewhere a hole, excess hole will be there, because initially equal number of electrons and holes are there. Initially the hole and electrons numbers are equal. Since we dope with boron atom, let's say for simplicity, in order to explain, I say I dope only one boron atom. So if I dope only one boron atom, this boron atom accepts an electron from the crystal and this boron becomes minus charge. So, and also there will be excess hole. So hole is plus charge and this boron is minus charge. Plus 1 and minus 1 again cancel. So again the crystal will be neutral, right? Okay. So either it's a n-type semiconductor or p-type semiconductor or intrinsic semiconductor, the total charge will be 0. The net charge is 0, or we can say the crystal is neutral. Okay. Right. So I think in the last class we started, we wrote the topic PN junction. Right? So PN junction, or we can call PN junction diode. So a diode is basically a PN junction. A diode is basically a PN junction. Okay. Right. So a P-type and N-type semiconductor are brought into contact with one another to form a PN junction. Okay, I think from there only we stopped the last class. Okay, so I think you wrote this line, right? A P-type and N-type semiconductor are brought into contact with one another to form a PN junction. So a PN junction is made of, you take one P-type semiconductor and N-type semiconductor, and then you contact them together. You brought these two pieces to you contact these two pieces so that it will form a PN junction. Okay. It's not. Guys, can you see the video? Drop me a text through chat box. I have shared a video to YouTube. Can you see that? Please drop a message in the chat box. Usman, can you see the video? Please, somebody respond. Okay, thank you. Okay, so here we have a p-type semiconductor. So this is a p-type semiconductor. So here E, this is a free electron, and this black color balls are holes. So we know in p-type semiconductor, the hole concentration is greater than the electron concentration. So number of holes is greater than the number of electrons. So therefore, here you can see there is more black balls, holes than electrons. Okay. And here you can see this is a n-type semiconductor. So in n-type semiconductor, you can see there are more free electrons than holes. Okay. So here we have in p-type semiconductor, we know there is more hole concentration than electron concentration. In n-type semiconductor, there is more electron concentration than the hole concentration. Now let's see what will happen if we bring those two conductors in contact. Okay. Okay, so here we are going to contact these two semiconductor pieces. Okay. So once we contact this, what will happen is, now you can see here there is more holes. Here the concentration of hole is greater. Here concentration of electron is greater. So when we bring these in contact, what will happen is these two we can see there will be a concentration gradient. There is a difference in concentration. So there will be a concentration gradient, so that in chemistry class you may have studied. If there is a concentration gradient, the particles will move from higher concentration to lower concentration. Are you all aware of this? If yes, please drop message yes. What about Sithira? Sithira, are you aware of diffusion? Okay, so I got a message from student. We have that concept in bio too. I think the diffusion is there in O level as well. Not, when I was studying, it was there, but now I'm not sure about the syllabus of O level science. Okay, so diffusion is when there is a difference in the concentration, or if there is a concentration gradient, the particles will move or flow always from higher concentration to lower concentration, right? So here now we can see in P type there is a high hole concentration, and N type the concentration is of hole is small. So therefore the holes will propagate or flow from P type. The exact word is diffuse. The holes will diffuse from P type to N type. And similarly, if you consider there is more electrons in the N type semiconductor than in the P type semiconductor, therefore electrons will diffuse from uh, N type semiconductor to P type semiconductor. So what happens as soon as we in contact these two? Okay, so what will happen is, yeah, okay, so these holes will move this direction. Okay, okay, the holes will move from here to here. It will diffuse. So there will be a diffusion of holes, right? So holes diffuse to this side, and electrons will diffuse to this side. Electrons, I put E. Okay, so we know now in electricity you have studied that current is a flow of positive charges. Current is flow of positive charges. Current is the flow of positive charge. Now what here happen is, now here hole is moving from this direction. So therefore I can consider this as a current, small current, due to the diffusion. Let's say I'll mark this as simple I1, or else I can consider okay, I'll take I1. So this will be small current due to holes, and electrons are moving this direction means, okay, okay. So here you can see holes are moving this direction. So we can think a current I1 is moving this direction, and electrons are moving uh, in this direction from here to here, as I have indicated here. So if electrons are negative charges, electrons are moving this direction, again we can think positive charges are moving, or current is moving in this direction. So we can take this I2. So you can see this both I1 and I2 are in the same direction. So I1 is the small current due to the movement of holes, the flow of holes, or the diffusion of holes. So I2 is the small current due to the diffusion of electrons. So by considering this I1 and I2, the resultant sum, I can think that that is the net, or the total current of I D. That is the diffusion current. Diffusion current. Diffusion current. So this current ID is due to the diffusion of electrons and holes as soon as we connected the p-type and n-type semiconductor. Okay. Did you understand what is diffusion current? Say, drop a message yes in the chat box, please, because this is very important. Yes, the diffusion current means the resultant current. So as we can see, there is a I1 current due to the flow diffusion of force, and I2 current due to diffusion of electrons. Then if we consider the resultant current, that is I have marked as capital ID. So that is the diffusion current. Okay, right. So if you understood that part, then we can go jump to the note. Okay, here. There's a nice button. Okay. Okay, so you can write the topic diffusion current in brackets. So write down diffusion current ID. So you can write down this. Initially, there is a very large density of gradient in both electron and hole concentration. Okay, I'll explain and go through this. Okay, so because I have already shared this PDF in the note. If you couldn't write, you can write it down later. Okay, so because I want to make this class more effective, so yeah, initially there is a very large density gradient electron and hole concentration. Initially means as soon as we contact p-type and n-type semiconductor, right? So here what we are going to discuss is as soon as we contact both n-type and p-type semiconductor. So initially there is a very large density gradient in both electron and hole concentration. So majority carry electrons in the n region. N region means n-type semiconductor region will begin diffusing into p region. Okay, and majority carrier holes in the p region will begin to diffuse into the n region. The diffusion of these electrons and hole is called diffusion current. Okay, the overall result of this diffusion of electron and hole is known as the diffusion current. Okay. Okay, if you have any questions related to this, you may ask. You can ask me. So if you want to unmute and talk, please you can drop a message as something like wanna talk, okay? Because I won't be able to listen to you because I'm using this mic here in order to have a clear audio. So if there's anything like while doing the class, like if you want to ask simple question, you can ask, type and ask very shortly. But if you want to ask a big question, you won't have enough time to type everything, right? It will annoy you, right? So in such cases, what you can do is you can just simply type need to talk or want to talk, something like that, so that I will allow you. I will remove this mic and I will unmute and talk. Okay, right. Raise your hand if you understand what is diffusion current. Please raise your hand. Okay. Sithira, did you understand? Yes, good. Okay. The next topic, reverse current. So again, I will explain you that. Okay. So now we know what is diffusion. Okay. So diffusion happens. Okay. When diffusion happens, what will happen is, so now you can see the electrons will move from n type to p type and holes will move to p type to n type. So this one of the free electron and hole, if they meet each other, what will happen? So the electron will occupy that hole. Electron will fill that hole. Okay. So actually, what we say is it's called recombination. So hole and electron. So one electron and fills this wall. So then it is recombination. So when this recombination happens, so that electron and hole will be no longer there, right? It will become a bond, right? It will complete the bond. So that what happens? It will make a. It is called recombination, right? Okay. So what happens is, again, I'll explain you the. I'll show you the this thing animation. So this holes and electron recombine, and then this region is becomes empty with mobile electrons. This or else we can say it will depleted with mobile electrons or holes, right? So as soon as these electrons are diffusing, electrons and holes diffuses, as there will be diffusing current, there will be a small built-in electric field, right? There will be built-in electric field, right? So here I'll explain you part. Okay. So what will happen is, now this side, this as electrons hole move to this side and electron move to this side, the hole and electron will recombine. So when it recombine, what happens was there will be left only the now we know p type is doped with uh, group 3 elements, so it is negatively charged. So if an electron fills that hole, it becomes a negatively charged, and then this becomes a positively charged. And so here this side it left with positive charges, this side left with negative charges. So what happens is, so we know if there is a, like for example, you can think of a capacitor or parallel plates, right? So this side is become positive charge, right? This plate is positive charge, this plate is negative charge. In electric field lesson, you have studied that there will be an electric field from positive to negative charge, right? There will be a positive plate to negative plate. So likewise, then there will be an electric field in this direction. There will be electric field in this direction. So due to this electric field, what happens is, due to this electric field, now let's say if a hole is, now we know if there's electric field in this direction, uh, positive charges plus charge will experience a force in this direction. Negative charges will experience the force in opposite direction to the electric field, right? So then if a hole, let's say due to the concentration gradient, hole is diffused in this direction. Now, at the same time, now the small built-in electric field is produced starting from zero. So due to this electric field, what happens is, now let's say a hole is comes here. Now there is a built-in positive charge here. So now there will be electric field from here to here, right? Starting at the initial, at the beginning, this electric field is zero. As soon as this diffusion occurs, only the electric field is increasing from zero, right? So once, now if a hole comes to this side, due to this electric field, now this hole is also experiencing electric force in this direction. So due to this electric force, now holes will move again to this direction, right? So this is due to this built-in electric field. Okay. Okay, so again, I'll explain now. Due to the diffusion of electrons and holes, there will be a diffusion current in this direction. As this electron diffuse, there will be a depleted region. So, so there will be left with donors and acceptors. We know acceptors are negative charges and donors are positive charges, right? Now, as the electrons and holes diffuse, we know there will be small built-in electric field in this direction, E. Now, due to this electric field, now let's say another hole is diffused into this direction. So this one experience a force in this direction. So therefore, there will be a slight movement of holes in this direction. So therefore, there will be a slight movement of holes in this direction, electric field direction. So then the holes are moving to again towards the P type. So there will be a small current in this direction due to movement of holes. So that one, let's take, I'll mark it as simple I1. Right. So this is we call as drift current. Drift current in electric field lesson you have studied drift current. When electrons are moving through a conductor, there will be average speed. That speed you know as the drift speed, drift velocity. So now likewise, this is a drift current. That's a normal current. Okay. So that is due to this electric field. Let's take this is I1, that is the motion of holes due to this built-in electric field. Now similarly, if I consider one of this electron moving this side due to the diffusion, right? And then this electron will experience a force. This electron will experience a force in this direction. We know electrons experience force in opposite to the electric field. Then there will be a movement of electron in this direction. The electrons will move into this direction due to this electric field. When electrons are moving this direction, means we know we consider the current as the opposite side of the movement of negative charges. So electrons moving this direction means the current will be there in this direction. So this current, let's take it as I2. So I1 is the drift current due to the movement of holes. That is due to built-in electric field. And I2 is the drift current due to the movement of electrons. That is because of this built-in electric field. Now you can see this I1 and I2 are both opposite to the electric field, or both are opposite to this ID, diffusion current. Okay. So then overall net I1 and I2 overall current I can mark as in this direction, simple I, okay, I'll mark it as capital IR. Okay. The R denotes reverse. It's a reverse current. You can see if it is the hole is reversed by the built-in electric field, or the movement of electron is reversed by the diffusion electrons movement is reversed by this built-in electric field. Therefore, this is known as the built reverse current. So, reverse current is this drift current of this electron and drift current of holes, and their overall resultant effect we can consider as IR, which is the reverse current. Okay, now please drop me a message in the chat box honestly whether you understood this IR or not. Uh, Uzman, is it clear for you? What about Sithira? By the way, who is that joined us? Okay, she has changed. Yeah. Okay, now good. Seems everyone understood. But again, I will explain one more time. Okay. Okay, so we studied what is diffusion. Diffusion is due to the concentration gradient. There is a large concentration gradient as soon as we connect the PN type semiconductor and N type semiconductor. Due to this concentration gradient, the electrons diffuse from N side to P side, and as well as holes diffuse from P side to N side. Therefore, as resultant, we can consider there is a diffusion current in this direction. As soon as electrons diffuse, holes and electrons will recombine. So as a result, there will be a left of positive uh, donor atoms and then negative acceptor atoms. So once this is being generated, there will be a slight built-in electric field. So initially the built-in electric field is zero. Now, for example, if I plot the graph of built-in electric field versus the built-in electric field versus the time, right? So, so this initially it's zero, but once the diffusion occurs, gradually this will increase. So this time is very short time, something like in the range of microseconds, the range of microseconds. So within microseconds range, it will the built-in electric field will increases. Okay. So as soon as this built-in electric field is being constructed, so what will happen is, now if another hole, like let's say trying to diffuse this, so due to this built-in electric field, this hole will experience a force in this direction, so that the hole will move or drift towards the p-type semiconductor. So there will be a small current due to that flow motion of hole. So that one we can consider as simple I1. Okay. Since now you can see the hole is moving from here to here, but due to this built-in electric field, its movement is reversed, right? Okay. And then similarly, if one electron is moving from here to here due to diffusion, but again this electron will experience a force in this direction in the electric field. Now again this electrons will move in this direction. You can see in this direction. Therefore, there will be a small current in this direction due to this reverse movement of electron. We can consider that I2. So then there will be small current. This I1 is due to the reverse movement of holes or the drift current of holes. I2 is the reverse movement of electron or the drift movement of electron due to the drift moment of electron. Then overall, we can consider there is a reverse current. We can name it as IR, reverse current. Right? Okay. Okay, so if you understood, we can write down what is reverse current is. Okay, so let's move on to the note. Okay, so write down reverse current. We can symbolize as IR. Okay, so here as electrons diffuse from the N region, positive charge donor atoms are left behind, right? So positive charge donors will be there. Similarly, as holes uh, diffuse from the P region, they uncover negatively charged acceptors. The net positive and negative charge in the N and P region induce an electric field. Induce an electric field in the region near the junction. Okay, in the region near the junction. This region is actually known as depleted region. There are two names. One is depleted region. Depletion region. Depletion region. The depleted means like Atugaladan. It's no longer there. Now, for example, dust is there means Atugala can no more dust is there. Likewise, depleted. It's completely depleted means no more mobile charge carriers are there. So that region is depleted with mobile charge carriers. So in that region, there is no mobile charge carriers. So depletion region, or we can call it as space charge region. So there are two names, depleted region or space charge region. Okay. Right. The net positive charge and negative charge in the N and P regions induce an electric field in the region near the junction in the direction from the positive to negative charge or from the N to P region. Now, due to this built-in electric field, minority carrier holes from the N region will move across the junction to P region, and this motion is opposite to diffusion current. Therefore, it is called as reverse current. Therefore, this is called as reverse current. Also, magnetic carrier electrons in P region will move to the other region across the junction. So initially ID is larger than IR, right? Okay, so that one I'll explain you here. White portion. Okay, so initially, okay, so here I take this as ID, diffusion current, and with time, and this is IR with time, and then I will draw another graph. Okay, so here if we consider this, the diffusion current is initially large concentration gradient. The concentration gradient is maximum, so therefore the ID diffusion current start with a maximum value and then gradually decreases as the diffusion occurs. We have studied that in the chemistry also. The rate the rate of diffusion will decrease. Okay, therefore the ID is initially starting with the maximum value and it decreases, right? And then IR start initially there is no electric field. Once this diffusion occurs only the electric field is will be there. So starting from 0 it will gradually increases, right? So this decrease and decrease, and then it won't go to 0, it will comes to a constant value. Likewise, this IR also comes to a constant value. This is because now you can see here ID starting with a maximum value, IR starting with a 0, and with the time ID decreases, IR increases, and then they have become same value. They will get equal once they both the values become equal. The number of electrons going to this side is equal, or the current to this side is equal to the current is the other side. So they will become a like dynamic equilibrium. So that ID and IR becomes a constant value. So if I draw these in the same graph, it will be like So both will come to a concern, this ID and this IR. By the way, these graphs are not there in our syllabus, so no need to write this down, okay? But you have to understand the fact initially ID start with the maximum value, IR start with the minimum value, and then they are gradual. This ID is gradually decreasing, this gradually increasing. That is the important thing that you should understand. Okay. Okay. So here again, this is a P-type semiconductor. Okay, and it has more holes than electrons. So you can see the solid balls are electrons and these circles are holes. Okay, so since boron is group 3 element, so it accepts electron. So then more hole concentration will be there than the electron concentration. Therefore, this is a P-type semiconductor. And now here this side, this is a N-type semiconductor. So in N-type semiconductor, we know there is more electrons than holes. And then once we connect these two, what happens? So initially, before connecting, the holes will move randomly, and the electrons and holes move randomly. So you can see here in the P-type, there is more hole than electrons. And similarly here in N-type, more electrons are there than holes. Okay. Okay, still the two materials are not connected. Now let's see what happens when we connect these two type of semiconductors. So we know the diffusion will occur, right? So you can see shortly the diffusion will take place. Okay, so holes diffuse to this side and electrons will diffuse to the other side. And then you can see here electrons and holes, they will combine, recombine. Okay, so this is known as recombination, right? So once they recombine, that region becomes depleted. Okay. Uh, check if it is. Okay, so will both reverse current and diffuse current will be equal in magnitude? Yeah, as I told you, the reverse diffusion current, initially diffusion current will be only there, right? So diffusion current will start with a maximum value, and as the diffusion occurs, the reverse current start with 0. And then what will happen? Then diffusion current will decreases, and then reverse current increases at a particular time. Both will be equal. Then they will come to a dynamic equilibrium. The whole number of holes moving to the other side is equal to number of holes moving to this side. So there will be a dynamic equilibrium. And what happens as they move, the recombination completely occurs. No longer current will be there. If completely recombination occurs, if the fully that depleted region, fully depleted with these mobile charge carriers, then no longer current will be there. Okay. And then in the graph I showed you, it comes to constant value and then comes to constant value, and then it will drastically drop to 0. Yeah, when the IR and ID are equal, the net movement of current is 0, right? So as you can see, what happens, they will come to a dynamic equilibrium. When it comes to dynamic equilibrium, at the same time that the recombination occurs, so fully that region, when it becomes depleted, then no longer current will be there. Okay, that this current IR and ID will be there only for some millisecond of time or microsecond of time. Okay, so here in this animation, they are showing this diffusion here. They are here explaining why it is not here also large holes concentrations there compared to electrons, but why it is not diffusing from here in this end. Here it is not diffusing from back this area or this area, because if you consider the nearby area, the concentration is, there is no gradient. So have same concentration. There is no concentration gradient. Therefore, it won't diffuse from here. Now, if you take here only, there is a difference in concentration. Therefore, it will diffuse from here to. Understood? So that's what they are explaining in this animation. Okay, so once they diffuse and recombine, so here you can see there is no mobile mobile charges, which means holes or electrons. So this region will be depleted. Depleted means no longer there. It's completely empty, right? So depleted. So this region we can call as depleted region or phase charge region. Okay, so here they are explaining about the reverse current. If this, we can see as the holes diffusing to this side, okay, as the holes are diffusing to this side. Now, due to this electric field, this side is plus, this side is minus. Due to this electric field, it will experience a force in this direction, no? Sorry. As you can see here, these three holes are diffusing to this side, but due to this electric field, this side is plus, this side is minus. These will experience force in this direction. Okay, so then they will go this direction. So here electrons also trying to diffuse to this side. Okay, so here you can see. Let me show you. Okay, that should be in the Okay, so here, uh, right. So if you take a mobile phone, if you are charging your phone, right, you know the current comes to our home as an alternative current from from the power station to our home, domestic home, uh, or if your fan is working, like a fan is also run with alternating current. But now when we connected the charger, right, now how we can charge the battery? I mean, the battery of a phone. Sorry, I got a call. Okay, so like if we have alternating current, then how we'll be able to charge our battery? If you want to charge a battery or a capacitor, you need to have a direct current, DC current. You should have a DC current. So in order to gain a DC current, what will happen here is inside this part, here we have a rectifying circuit. So in order to make a rectifying circuit, we need diodes. So those things we will learn in our upcoming sessions. So we use diodes to rectify or convert a alternative current to a DC current. In order to convert alternative current to a DC current, we use combinations of diodes. Okay. So if we use one diode, we can rectify half wave rectifier. If we use two diodes, it's a full wave rectifier so that we can get a DC current. Those things we will learn in our future class. Okay. Probably, I think maybe in our next class we will be able to learn about. By the way, today what I discuss this diffusion current and reverse current. In other all classes, they will just say diffusion current is this, reverse current. I think they won't spend more than half an hour to discuss about what is diffusion and what is reverse current. In fact, honestly, I'm saying during when I'm studying also, I didn't have a proper idea what is diffusion current and what is reverse current, because in school and as well as in my class also, they just very fastly explain what diffusion and reverse current. Okay. So, but understanding this is very important because these are the underlying principal mechanisms of diodes, right? You don't understand what is happening here, then you won't understand what is forward bias, what is reverse bias. So, our next topic will be biasing a diode and the forward bias, reverse bias. So, in order to understand that very well, we should have to have a clear idea about what's happening inside here. Okay, so that's why I'm spending much time on this, because these are the very underlying principles of all electrons. Okay, even if you take a transistor made of uh, two p-n junction. Okay, so there also, then you have to understand the mechanism here. Okay, this mechanism. Okay, so okay, so here again, discussing about the diffusion current and reverse current. Keep this part. Okay, so diffusion current will be the in direction towards this side, and then there will be reverse current due to built-in electric field. So the reverse current also drift current. So You can see they have using the word drift because it's a normal current due to the electric field. When you supply a potential battery connect to a battery, there will be electric field. I mean, if you take a normal electric circuit, if you connect to a battery, there will be a electric field. Due to that electric field, there will be a current. So that is actually drift current. Okay. So a similar kind of current is there. That's why it is known as drift current or the reverse current. So you can see there is an electric field from this side to this side within this depleted region. So in the depleted region, there are no mobile ions. There are no mobile charges, no holes or free electrons. We can see only the so within this region, we can see only the donor atoms and acceptor atoms are there. So boron is a acceptor atom. This is a boron atom. So this negative charge, this positive charge. Okay. So if you consider this side, it is electrically neutral, and this side is electrically neutral. But here this has a positive charge, here has a negative charge. Therefore, there will be electric field from inside to P side. So that is called depletion region or space charge region. Okay. So suppose now if I know now usually this depletion region has a thickness of micrometers, right? Like several micrometers, like 10 micrometer or 12 micrometer. It's in the range of micrometers, right? This depletion region, even though you have drawn it like very thickness, right? That is in the purpose of explanation. But in reality, this depletion region is very small in the range of micrometer. Okay. Okay. So here, this part I'll explain. Now we know there is electric field in this direction, right? There is electric field in this direction. So, and I think in electric field lesson, you have studied that there is a electric field. Now, even in capacity, know the distance, we can find the potential difference, right? So, now let's say this gap is simple D. Then the potential difference V equals E divided by D, where E is the electric field, the induced electric field or built-in electric field in this space charge region, in this depletion region. D is the thickness of this depletion region, and therefore there will be a potential, electric potential. This one I hope you have studied in the electric field lesson, right? So the potential difference is given by uh, the gradient, electric field, right? The actual definition for potential difference V equals to minus delta E over delta D. Sorry, I wrote the equation wrong. Sorry, it has to be E equals V over G. Electric field is equals to E over G. Right? E equals electric field equals V over D. Because it is not electric gradient, potential gradient. With the potential gradient, that term only I understood. Okay, I had. So in actual definition, E equals to minus delta V over delta D. So this part is there in electric field lesson. You have to draw the variation of electric field by considering the potential gradient. Okay. Anyway, just considering the magnitude, we can write E equals V over D. Right. Therefore, here V equals E into D. So this built-in electric field, once they reach to a equilibrium, or if it is completely depleted, at that time this value E will be constant, and then the thickness of this will be constant. Therefore, this constant, this potential is known as the barrier potential. Now, suppose if an electron, like hole, suppose if a hole wants to move from, let's say, suppose if a hole want to move from here to here, right? It has to do work against its electric field, right? So it is a barrier. It has to overcome that potential to move from this side to this side. That means if I want to send a positive charge from here to here, then I have to give a work or supply energy, right? That should have this value. So now this has a value. Now, for example, let's say this silicon crystal, then this V is roughly 0.7 volt. This potential difference, this barrier potential is 0.7 volt. Then if I want to move a hole or positive charge from this side to that side, then I have to do a work, right? I have to give energy that is equals to a minimum 0.7 volt, because the volt, the potential, the definition of potential is, electric potential is the amount of work done is needed to move a +1 coulomb charge. So here you can see here this in the right corner, here they are used, here is potential. They have explaining, I think they are explaining the definition of potential, right? The definition of potential, I think you have studied in electric field lesson. Electric potential is defined as the amount of work done necessary to move a +1 coulomb charge, right? That is the definition. Now, now for example, if there's a current, let's say in a wire, right? So if I take a wire, the current moves from higher potential to lower potential, right? I hope you guys seeing my camera. So if I take a wire, so current moves from higher potential to lower potential. So if I say the potential difference between these 2 points, the potential difference between these 2 points is the amount of work done necessary to move a +1 coulomb charge from this point to that point. That is the potential difference. Okay. So likewise, now if you want to move a hole or plus charge from this side to this side, you need to apply a minimum of 0.7 voltage, right? You have to apply that voltage, or you have to overcome that barrier, right? So these are all very important. Now, our next topic we will discuss about biasing a diode. Like if you want to forward bias, you want to apply minimum 0.7 voltage. So these things are very important. Okay. Okay. Do you all understand this? If you understood, raise your hand. Okay, Akil understood. Usman understood. Yeah, good. You can see the hand raises. Yadursha, did you understand? Can you let me know through chat box? Okay, good. Thank you. Okay. So we can move on to the note. Okay. So potential barrier, BD. Okay, so let's go through the note. As soon as charge flow across the junction, the diffusion current will decrease with time, while the drift or reverse current increases with time. Eventually, at an instant, ID will equals to IR. So it reaches to an equilibrium, producing a potential barrier, approximately 0.7 volt for silicon and 0.3 volt for germanium. Okay, so I think this is the video that we was watching. Okay, and then so write down potential barrier VD, VB. So initial so it reaches to an equilibrium producing a potential barrier. Okay, once this potential barrier is comes to saturated, so no longer current will be there, right? So actually what happens is now I'll drawing here. So you can see the whiteboard. So more like this. This is my graph is not so accurate, just to give a rough idea. So here, let's say I current and the time. So diffusion current decreases with time, ID. And then with time, this IR will increase. And then they will come to a equilibrium, right? When these two are equal, okay, when they come to equilibrium. So this is IR. And then here at this moment, ID equals to IR. I'll write in the subscript. So ID equals IR. So once they get to that value, and then gradually they will decrease to 0. This is not, just to get your idea, this is not the exact graph, right? Because there is no anything to draw with ID and IR in our syllabus. And also there is nothing like that study. Just to give you a rough idea. So once this is reached, and then they will drop to 0, right? And then when it becomes 0 also, that is still, there is a, it is not suddenly getting to 0. So still here also, there is a diffusion is up there, reverse current also there, diffusion, reverse current occurs, and then they gradually quickly drastically falls to 0, right? Okay, so no longer then current will be there. Okay, so the next topic, depletion region or space charge region. The region on either side of the junction now become completely depleted of any charge carriers. So depleted means there is no any charge carriers, empty. Like Atugala Dana, its meanings in Sinhala, if it's got, it's like you're removing out of it. Right? So this area is called the depletion layer or space charge region. This is about 1 micrometer. So it's in the range of 1 micrometer. 1 micrometer means 1 meter you divide into million. So that means 1 millimeter you have to divide into 1000. You get 1 micrometer, right? So that is very small, thin, narrow layer. Okay. Okay. So here this is the variation of electric field and the uh, potential. So this depletion region, in this region, so you can see the variation of potential. So this side potential is plus, electric potential is plus. Here this potential. So if you consider the difference, if you consider the difference, this difference is actually like, so I'll show you here. So okay, this value and this value, the gap, this value gap is the VB, potential barrier. Okay, the difference is the potential barrier. Okay. So this graph, you should, it's there in the syllabus, you should know. Okay. Okay, so here you can see in the depletion region, here more plus charges. So here plus potential. Here more minus charges, so minus potential. Okay. So here at this point, at the mid of both the depletion region, you can consider the it is zero potential. And the variation of electric field. So here field is zero because we consider the p-type, this region is neutral, right? So here it will be zero, and then the gradually increases at the middle. Electric field is maximum, so it has a negative value, and then here again it will be zero, and then here zero, because in the n side, this side also it has a uniform distribution, and this is rho is actually, I think, potential electric field to rho. Okay, so here this potential, uh, here this one is, sorry, I have mistaken. Okay, so here I'll explain you this. Okay, so you have in syllabus this graph and this graph. Okay, but this graph is not there in the syllabus. This is the charge density. This is actually rho is charge density. Charge density. Okay, so here charge density is plus. So Q into Nd. N is number of Doan atom. Q is the charge of a Doan atom. So total charge is Q into Nd. So here capital N is number of Doan atoms. Here capital N is number of accept atoms, right? So minus Q times Na. This is the charge density. Okay, and then this is the electric field intensity. So here you can see here the gradient, the charge. If you consider the charge, the difference is maximum at this point. Okay, at the middle. So their electric field is maximum. So therefore here the gradient will be maximum because potential is the potential. Okay, this is the potential. You can take as V axis potential, right? So here this is the VD potential, barrier potential. Okay. So here the first graph is not there in the syllabus, but still you should be able to understand. That's not a much deal, right? Here plus charges. So here therefore plus charge. Okay, we consider uniform charge distribution. So there is a plus charge. So here charge is plus. In here charge is minus. And then this region is neutral, so it's zero. This region also it's neutral, so it's zero here. Okay. Right. You have to draw this graph. You can see in your I'm having a headache. Okay. So far what we discussed is the underlying principle of PN junction or underlying principle of diode. Okay. So now we can move on to the topic diode. So write the topic diode and then subtopic an ideal diode. Okay, so here before getting into that, now here we have drawn this graph. So this is actual real case scenario. This graph electric field and the this potential, the variation of electric field and potential here is the real case scenario, right? And then we can draw the graph of ideal. Okay, so this is the graph of ideal. Uh, Ideal diode. So for ideal diode, it will be like this. Now here, by the way, I have to explain you this. I should take these two into the same. Okay, now here, no, still it's not. Okay, so for ideal diode, it will be like this. So here, this electric field, variation of electric field, or variation, this is a variation of potential. Now here we have electric field is in this direction. The electric field is this direction. So that means we have considered the electric field is positive in that direction, right? So here in this graph, it has considered the electric field positive in that direction. If we consider it is in positive in this direction, then therefore maybe I can draw this as like this as well. So here E, and this is distance. So then I can draw the graph. Okay, so here we can draw this like in such case. If we consider field is positive in this direction, but here this actually in this direction, so it is negative. So if someone draw like this also, right? Okay. Okay, that's considering the direction because it's a vector quantity. Okay. Okay, so the circuit diagram, sorry, circuit symbol of a diode. So here it should be so here you should write the circuit symbol of the circuit symbol of a diode. So circuit symbol is so this side plus, this side minus. So plus we usually take to the p type. This is for the n type. Okay. P this side n. Okay. So far we have discussed zero bias diode. That means PN junction without connecting to any external power supply, right? that is the PN junction is not connected to any external voltage source. Okay, right. So now what we are going to discuss is biasing a diode. So there are two type of biasing: forward bias and reverse bias. Okay, so first let's discuss about forward bias. So in forward bias means for the P side of the PN semiconductor, we give the plus. So here plus side of the battery is connected to P type, and negative side is connected to N side, right? So this is forward biased. So if you write in the circuit symbol, so this is the case, right? Okay. Okay, in forward bias, the positive terminal of the battery is connected to the P-type semiconductor material, and the negative terminal of the battery is connected to N-type semiconductor material of the PN junction diode. Okay, so that is the forward biasing means. Forward biasing means the positive side of the positive terminal of the battery is connected to the P-type semiconductor, and the negative terminal is connected to the N-type semiconductor. Right. So when we connect this there is three scenarios. There will be three cases. So we'll discuss each of these cases. So first case is now this Vs comparing with Vb. So one is Vs is less than Vb. The supplied voltage is smaller than the barrier potential. And second scenario, Vs equals to Vb. So we have applied we have connected the variable battery, right? So let's say we are increasing this uh, external voltage from 0. Gradually we are increasing. So initially it has small value 0 and 0.1, 0.2, that gradually increasing. So at the initial condition, the Vs supply voltage is less than this barrier voltage, right? Now you all know what is barrier voltage means, right? When there is a when the depletion region is created, there is a building field. The corresponding voltage value is the barrier voltage. If you want to move a charge from this side to that side, you should give a energy that has minimum of that barrier voltage value, right? So and the third case where Vs is greater than Vb. So let's discuss each of these cases, right? So when Vs is smaller than Vb, right, the battery will push the electrons or the charges. Now I can't say on electrons, free electrons or electrons. Uh, in a word, current. The battery is pushes the current in this direction, right? It pushes. By the way, there is no any current here since Vs is smaller than Vb, so there is no any current. Actually, what happens is this is pushes the charges to this side with some value, let's say 0.2 volt, but still there is now let's say this is a silicon, this PN type P type PN uh, junction is made of silicon material, then we can say it has a barrier voltage of 0.7 volt. So this supply voltage pushes the charges with 0.2, right? Now for example, it's something like what you call tug of කබා දිනවට ඉංග්‍රීසි මොනවද කියන්නේ? Tug or what? I don't know that word. Like uh, like like there is a rope. Few people are in this side, few people are in this side, and the game. What is the game? Anyone name? It comes tug of war, tug of war. I'm not sure. Okay. If anyone knows that word, can you drop me in chat or in the chat box? Tug of war. Thank you, thank you. I got a concept here. So in tug of war, let's say you are like let's say tug of war between you and your friend. You are pushing this side with like 2 Newton. Your friend is pushing that side with 7 Newton. So it won't come to your side, right? Likewise. Now here this pushes with, now it's like a barrier voltage. Now here this barrier is there. It's like a wall, right? This wall of height 0.7 voltage. Now this one has applied 0.2 voltage. So then this charge which is at here cannot go through this because the energy is not enough. So in order to move, it has to apply a minimum of 0.7 voltage. Then only this electron can move from this side, right? Okay, so then what happens? So only when what will happen is there will, due to this applied voltage, there will be small current. There will be small current. It will recombine, and then the voltage across this will be decreased. So 0.7 minus 0.2, it will be now 0.5. Okay. So here, when applied voltage is less than that of barrier voltage, the PN junction is not really biased for the current to pass through. Therefore, there is no current in the circuit, and the potential difference across the junction will be VB minus VS. This will be the potential difference, right? And here one more thing happened, the thickness of the space charge region will decrease, right? The thickness of the space charge regions will be decreased. And the depletion region will be thinner, yeah. And the depletion region will be thinner. Okay. The more voltage you apply, the more the width of the depletion region is reduced. Okay. So here when we apply this Vs, there will be a small movement of minority carriers. So that therefore the thickness of the depletion region will decrease. Okay. And then it will decrease to a constant value. That is corresponds to a voltage difference of VB minus VS. Now, for example, 0.7 minus, let's say, silicon, then barrier voltage is 0.7. I have applied a voltage of, let's say, 0.3. So 0.7 minus 0.3, 0.7 minus 0.3 is 0.4. So there will be a potential difference of 0.4. And we know E equals to, V equals E over D, right? So then what will happen? This V potential difference across the junction will decrease. This is also decrease. This one also will decrease, right? But the thickness, only slight change will be there. Okay. And now when we increase further and further, what will happen is the thinner the space charge region, or it's thinner and thinner and thinner. And then when Vs is equal to Vd, it's completely gone. No longer this thing is there. I mean, no longer the PN junction will be there. So it's like a normal conductor, right? It comes to a normal scenario. Okay. Okay, here the potential difference across the junction is 0, therefore there is no depletion region. Okay. And if Vs is greater than Vb, if the applied voltage is more than the knee voltage or the barrier voltage, it cancels the potential barrier and current will start flow. And we say that the junction is forward biased. So if you want to forward bias diode or PN junction, what you have to do is, first thing you have to connect the battery properly. The positive term of the battery should connect the side of the semiconductor. Negative side of the battery is connected inside of the semiconductor. And then you have to apply a voltage that has a value greater than the barrier voltage, then the diode will be forward biased, and then there will be a current in the circuit. Okay, so here this is the variation of versus V. I mean, okay, there is a small mistake. I think something went wrong with this VF. Wait, let me draw that here. Mhm. So I axis and here I and then V. Now let's say I'm drawing this for a silicon diode. So then the barrier voltage 0.7. So initially, if here IV characteristics means the current versus the apply voltage, supply voltage. That means the voltage of the battery. So here the diode, and here's the battery. The battery voltage will be the V. Okay. So if I draw that, so we can see initially if V equals 0, then obvious I is 0. Then if we increase gradually, there is small current which is negligible in the micrometer range, so microampere range. So microampere range current will be there. So, and when the barrier voltage, when we pass the barrier voltage, then there will be a current. So the current will increase with the apply voltage. Okay. So this is known as the IV characteristic curve of a diode when forward biased. IV curve of a diode. Okay, so and then reverse bias. Reverse bias is simply changing the terminal of the battery. So the negative side is connected to P and positive side is connected to the N. So this is circuit symbol. Okay. And then here when we reverse bias, actually we are supporting the depletion, right? The electric field due to the external voltage supply is in the same direction of the electric field of the barrier potential. So we are supporting the barrier now, right? As a result, the width of the depletion region is increased, right? So what happens is if you increase the VS more and more, the depletion region get thicker and thicker, it get increased, right? So if now we know the depletion occurs due to movement of now initial condition when we connect, as soon as we connected to p-type semiconductor and type semiconductor, the depletion region has built due to the movement of holes, diffusion of holes and electrons, and they recombine, right? So now what happens now if we apply a reverse voltage, again we are giving the more holes and electrons will move and diffuse, and they will recombine so that the diffusion depletion region gets more thicker. Okay, so that current, when we increase and apply Vs, the small current will be there due to the recombination. So that is known as leakage current. It is a small current that is also in the range of microamperes. Under reverse bias, majority charge carriers cannot carry the electric current. However, PN junction diode allows the magnetic charge carriers to pass through. The electric current carried by the magnetic charge carrier is very small, negligible, in the range of microampere. That is known as the leakage current. And then when we apply this, if we increase this reverse supply voltage, reverse bias supply voltage, more and more, at a particular time, the junction cannot withstand this, and suddenly entire thing is collapsed so that the junction breaks. So that particular value of the voltage is known as peak inverse voltage. Further increase in the reverse bias voltage at a certain value, the junction will break down and large current will flow. This corresponding voltage across the diode is called as the peak inverse voltage. So here's the here reverse bias. So current will flow in the opposite direction, right? So here it has a very small current. You can see it's a very small in the range of microampere. And then when it reaches when the voltage value gets to peak inverse voltage, the junction breaks and then large current will flow. Okay, it will comes to a large value. So this is the total IV characteristic curve. So here this part is forward biased and this part is reverse biased. So this is for real diodes, and then let's see how it's look like for ideal ideal case. So in ideal case, in forward bias, there is no potential of the junction, only the I will be increased. Okay. So this is case of ideal diode. Okay. So in reverse bias, no current will flow. So like resistance is infinite. Okay. And let's see the IV characteristic curve of a silicon and germanium. So germanium usually it has 0.3 or 0.4, and silicon it has a value of 0.7. Okay. So you can see even though they have current is in milliamperes, these current are milliamperes. And this side you can see it's in microampere. So this you can see nearly like 0.01 microampere. Okay. So today we discuss the mechanism of right after when we connect uh, two semiconductor pieces. One is p-type and n-type. If we connect p-type and n-type, right after that, what happens? We discuss that today. So as soon as we connected, due to the concentration gradient, diffusion occurs. As the diffusion started, the built-in electric field will be uh, created, and due to that, there will be small reverse current. So at initially, the diffusion current is maximum, and the reverse current is zero. And with time, diffusion current decreases, reverse current increases, and then they will come to a equilibrium, and then they will gradually decrease and become zero. And then at that time, no current is there. There will be a depletion region. Depletion region means there is no any mobile charge carriers. So no free electrons or holes in that region. In that region, only donor atoms and the acceptor atoms are there, right? Okay. So the when this completely depletion region comes to saturation, so there will be a corresponding potential barrier, potential difference, that is known as potential barrier for a silicon PN junction. PN junction made of silicon material, it has a value of 0.7. Okay, and then we discuss what is forward bias and reverse bias of a PN junction. Okay, so if you have any questions, you can ask. I will remove this mic. So if you want to ask to the yes. Do you have any questions? Okay. Okay, then so if you have no any questions, then if you don't have any questions, then you can wind up the session. By the way, did you understand everything? Yes. Okay. Okay, then so by the way, I have missed a question from Aki. Just saw in the chat box. So can we say depletion region is the region where recombination of electrons and hole take place as soon as diffusion of charge carriers took place? Yes. So in the depletion region, recombination occurs. So when recombination occurs, so there is no more mobile charge carrier, right? So what we discussed today is very important. Like if you want to understand diodes and transistors, even solar cell. So what we discussed, the mechanism, what we discussed today is the underlying principles of solar cell. Because solar cells are made of uh, semiconductor materials like silicon. Silicon, if you take in nature, silicon is, if you take a silicon lattice, it's a black color. So that's why like if you take all the solar cells, it has a black color in nature because black colors are more absorb energy, more heat absorbed, right? For example, silicon solar cells are there, cadmium sulfide solar cells are there. There are more solar cells like most of solar cells are most in black color because they absorb more energy. Because you know, black color usually absorbs more energy. That's why, but white color reflects more energy, more light or radiation. Black color more absorbs more. White color more emits or reflects, right? So these things you will study in a matter and radiation lesson as well. So that's why the school uniforms are made of white color, right? Because so that less heat is absorbed, right? Okay. So yeah, I was saying this. What we discussed today is the underlying principle of solar. In solar cells also, these are the basic principles. Okay, then so I'll wind up the session now. Good night. Study well. Take care. And by the way, tomorrow we have the paper class at 10 a.m. Okay, those who are coming to the paper class, so tomorrow we will have at 10 a.m. Okay, then good night. Bye. See you. Take care.